Hey folks, I'm Eric at LangChain, and today we're going to be talking about using MongoDB semantic caching in order to cut our LLM costs. Today, MongoDB launched their integration package with LangChain, so you can use MongoDB as a vector store or as a cache or even a semantic cache, which we're going to go through today. We're going to be using a few different providers in our solution. So the first thing that we're going to go through is kind of who each of them are. Then we're going to go through two examples from our cookbook, one just being a basic prompt and LLM chain with semantic caching, and one with RAG, where we'll actually discuss some of the challenges of using semantic caching with a retrieval-based system. So without further ado, let's dive in. The first orchestration framework that we're going to be using is LangChain, the company that I work at. These are the LangChain docs. We allow you to connect to any LLM, any vector store, different kinds of tools, and we're kind of a one-stop shop for all those different integrations, and then we provide some standard abstractions for those integrations as well as some other approaches. We have lots of cookbooks that allow you to implement academic papers or just kind of basic solutions, which we're going to be going through today. The next up is MongoDB specifically. MongoDB is a NoSQL database provider that also provides Atlas, which is a cloud database available in a few different environments. It has native vector search, which is the reason that we're going to be using it today. Semantic caching involves kind of an embedding lookup, very akin to a vector store retrieval step. So we're going to be leveraging the Atlas vector search instance there. And we're also going to be using some other providers as well. So we're going to be using Anthropic's Claude 3 LLM in order to actually generate some responses from our application. We're going to be using OpenAI's embeddings for this particular application, and when we get to the RAG step, we're going to be using Exa's search retriever in order to retrieve some documents to actually base our responses on. So let's dive in. The first chain that we're going to implement is the basic prompt and LLM chain from our cookbook. It's the first entry, and RAG conveniently is the second one as well. The idea behind this is it's really the simplest thing that you can do for getting started, and so we're going to make something kind of similar to that. So let's go into our editor. So the first thing you're going to want to do is you're going to want to install some packages. So today we're going to be using four main providers: MongoDB, Anthropic, OpenAI, and Exa. So we're going to want to install those four partner packages. So we can see those up here where you're going to pip install LangChain MongoDB, LangChain Anthropic, LangChain OpenAI, and LangChain Exa. The next step is we're going to want to set some environment variables in order to get those set up. I already have those set up in my environment, so we're not going to have to worry about those. We're going to be using OpenAI for embeddings in this particular example. And then last but not least, Langsmith is our kind of first-party observability and debugging tool at LangChain. And if you want to use that in order to debug traces, we can actually just quickly open that to see what that looks like. And just briefly showing what Langsmith looks like, we'll look at this a little bit more later with some of the further examples. It allows us to trace all of our different applications in order to see kind of how the prompt is constructed and which documents are actually retrieved as part of different retrieval steps, as well as other things such as kind of LLM pricing, token counting, those kinds of things. So we'll be using that down here, and you just need to set these two environment variables to activate that throughout kind of your entire LangChain application, which is quite nice. So once we have all of that set up, we can dive in. So first thing we're going to do is we're going to want to set up some sort of prompt into model chain. So the kind of way that we compose prompts and models, as well as everything in LangChain, is kind of through this runnable interface where we can pipe the output of a prompt into a model. Now let's configure what that prompt and model actually are. So first, we're going to want to set up our model, and we're going to use a chat Anthropic model using their new Claude 3 Sonnet model. So we'll say from LangChain Anthropic, import chat Anthropic. And actually, let's use Opus instead, just so we can show off some of the speed gains as well from caching. So Opus is Anthropic's largest and slowest Claude 3 model. If you want faster ones, you can obviously use Sonnet and Haiku as well. So we'll use Claude 3 Opus 240229. They have their nice leap year date in their model. And then we'll also want to set up our prompt. So in order to make a prompt, we'll do from LangChain core.prompts import prompt template. And we'll set our prompt to be prompt template.from template. And we'll give it a nice little string here. And we'll start with just a classic RAG prompt where we'll say answer the following question about the given context. And we'll give some kind of XML surrounded context. So the squiggly bracket context field is what we're actually going to substitute in as part of our prompt template. And then these XML tags are actually just there to indicate to the LLM that that is what the context is. And then we'll give a question below there. So that should form our prompt and our model, and we'll see if that runs. Looks like we successfully did that. And then we can now try invoking it with some sort of context and some sort of question, where we are essentially substituting in those two kind of blue variables from up here from whatever we set it to. So we could, for example, give it something like Eric works at LangChain with a question of where does Eric work? And we can see what we get back from that. And in 2.6 seconds, again, Opus is kind of a larger model. We can see that based on the given context, Eric works at LangChain. So looks like our basic chain is working. If I were to run this again, it should still take 2-ish seconds because it's going to actually send that API call to Anthropic every single time that we do this, as well as rack up token usage, as well as our good Anthropic bill there. So in order to kind of cut some of that, let's go into semantic caching. So caching in general, and I'll actually draw a bit of a diagram here. Semantic caching in general intends to kind of prevent us from sending too many API calls to our model provider. So in the chain that we just set up, where we have a prompt going into a model and giving some kind of output, what we're essentially going to do is we're going to create a kind of bypass path around the model step, where if we've seen kind of the formatted prompt before, we're actually just going to grab that from our cache. So in this case, we're going to be doing that with kind of a MongoDB based cache. And we're going to just get whatever response we had last time from that. And there's kind of two main ways that we can do that. So the first is with a regular cache, where we're going to be looking for an exact match of the formatted prompt. And this is good for instances where we know we're going to get very similar prompts from whatever system we're using. So in our particular example, this actually likely won't work particularly well because it's passing in a user's question as part of it, and then likely that context is coming from some sort of retrieval step, which we're going to add in a second. And so if I asked even something just slightly different, such as where did Eric work, period, instead of a question mark, it's actually going to not be able to look that up because it needs that exact match in order to look it up. And so the approach that we're going to be using today in order to make that work is called semantic caching, where instead of indexing by the kind of exact formatted prompt string, we're going to index by an embedding of it. So we're going to use embeddings plus a vector store. So we're going to use vector search to look up matches. And we're going to set some sort of threshold, because an important part of these systems is that if there isn't something with sufficient similarity, we actually do still want to call the model. And then, of course, at the end of this, we're also going to want to insert our record back into our database, such that we can actually access that the next time that we call it. So today we're going to be focused on the semantic cache implementation of Mongo, and we also have documentation on how to use the regular cache if that works better for your use case. So let's get started on adding semantic caching to our kind of basic prompt and model chain. So to do that, we're going to first create our semantic cache instance. So we're going to import that from the LangChain MongoDB package, and it's called the MongoDB Atlas Semantic Cache. Is what we're going to import. This relies on MongoDB's hosted Atlas solution in order to enable vector search. So note that if you're using open source Mongo, you might run into some problems using this. And then we're also going to want to configure which embeddings we want to use. So in our case, we're going to import that from LangChain OpenAI, import OpenAI embeddings. You can use lots of local ones from Hugging Face. Nomic has some pretty good embeddings. Voyage AI has a new embedding integration with us that we're really excited about. So you can kind of pick your embedding provider. We're just going to use OpenAI for convenience today. And then we're going to also import our good OS package so we can access some environment variables. I'm actually going to paste in some of the configuration that we're going to use for our vector search today. The first is we're going to load in kind of my secret Atlas URI as our connection string. This is Mongo's way of configuring kind of which Atlas instance to connect to, and it also encodes the password used to connect to it. So I have that set as an environment variable already. And then we're going to configure an index, database, and collection to connect to as well. So we can try running that to make sure we can actually load that. And then we're going to want to create our semantic cache as our semantic cache instance. We'll create our embedding as OpenAI embeddings, and we'll use their text embedding 3 small model in order to do that. We don't want to add any more dashes to that. And then we'll have our connection string as constring. We'll have our collection name as collection, our database name, and our index name in order to kind of wrap that up. And then last but definitely not least, we're also going to want to configure a threshold in order to make sure we're not returning things that are potentially the most relevant entry, even though it's not relevant at all. So that's something that we do in classic retrieval, where we actually always want to get kind of the 3 most relevant documents from our vector store. But with semantic caching, even if there are 3 entries that are the most relevant to our query, it's possible that those 3 entries are actually not relevant at all to us. So this particular index uses a cosine distance, or a cosine relevance score, and so we'll set our threshold to make sure it's greater than 0.99 in order to get that set up. So we can try running this, make sure I didn't have any typos, and then we should be good to go. So the first thing that we'll want to do is we'll actually just want to clear that cache. So the LLM cache abstraction in LangChain allows you to clear kind of all the entries in it. And so we'll do that just to make sure there's nothing in there to start. And then we'll want to set our LLM cache. So in LangChain, there's a kind of convenient way of setting that globally, so you don't actually have to configure this on each and every LLM call that you have. So we can have from LangChain core globals import sets LLM cache, and here we'll just set our LLM cache to our semantic cache object. And so this will allow us to cache our responses in that, as well as kind of get our responses back out whenever we've seen ones that are sufficiently similar through the semantic cache lookup. So we can try our nice question about where I work again. As expected, the first time we run it, this takes some time, where, again, based on the given context, Eric works at LangChain. And then if we run it again, we should already have an entry in our MongoDB Atlas semantic cache, such that it should be pretty quick. So let's try running it again, and we get our response much faster. So now let's try changing our query slightly. So let's add some comments here to make that clear. Same query, exact query, and then almost same query. So we can try an example where instead, where does Eric work question mark, we'll do where does Eric work period. Hopefully that will also be able to retrieve it. And then now let's try one that is different. So here we're going to instead ask something about the mayor of San Francisco is London breed. And here we basically want to make sure that we are not retrieving our Eric works at LangChain response, because in that case that would really represent a failure of our chain. So here, hopefully, it takes some time. So far, so good. And it looks like it's successfully making that LLM call. And now, if we ask something along those lines again, it should be quick because it's already cached from this prior step. So looks like our semantic cache is working on our basic example. We went through kind of what semantic caching is and why it's powerful. And now let's actually augment or create a new chain that implements RAG instead of like explicitly plumbing through the exact context that we have up here. So let's go through that, and we're going to use our exa search retriever from this. So we'll import from LangChain exa, import exa search retriever, and we'll also import a configuration option called text contents options. We can actually pull up the exa search retriever documentation, and the reason we're importing that is because we want to configure kind of a max length for each of the documents that it returns. So exa is an integration that searches the internet, much like Google, and returns documents from their index. And so some of the documents on the internet are quite long, so we're going to want to set kind of a max length for that. So let's create our retriever. I have my exa API key already set, and we're going to want to set our text content options to text content options of max characters as, let's start with 300 for now. Depending on the use case and the types of questions we expect, that might be a little bit short, but we can give it a go for now. And then we'll kind of create our chain from scratch again. So we'll actually use the prompt we already had because it plumbs in context and question, but we will start with a different step where we actually need to populate our question, which we can do as a runnable pass-through, and we'll have to import that from LangChain core runnables. So that's just going to pass through the exact string that we invoke our chain with through as the question. And then context, we're actually just going to pass that string into our retriever, and then we can pass that into a kind of format documents function, which we'll define up here, where that'll take in docs, and then we'll return, well, first we can get the contents of all those docs. So we'll get doc.page content for doc and docs. and then we will join those with new lines. So we'll just have a double new line, and we'll join all of those kind of content strings. So this is just kind of explicitly formatting that into a string. If you were to just pass in the documents directly, you might get some of the metadata that EXO returns kind of plumbed into your LLM as well, which in this case is probably not as desirable because that could be ordered differently, and especially since we're dealing with caching, it's better to just have kind of the whole string in there. So let's have that as the first part of our chain, and then we'll pass that into our prompt that we had above, and then we'll actually use the same model as well. So as a reminder, this chain, and we can actually draw this, that might be a little bit more clear. This chain is basically adding to the beginning of this one, where before this we want to populate both a question as well as some context, where the input before that is going to be coming in as just the question. So the first thing we're going to do is we're just going to plumb our question straight through. That's all the runnable pass-through does. And down here, we're going to pass our question to our exa search retriever. And we're going to pass the output of that into format docs in order to get our context. So here, again, we're kind of passing our question in as input to exa search retriever. And then in the middle here, this is going to be our kind of list of documents is what's going to be kind of passed through in this middle step. And then format docs is going to just turn this into a string where it just has all the contents kind of put together. Our prompt is going to turn that into our string of answer the following question based on the given context. That will become our formatted prompt. And then we're actually just going to use the exact same cache in order to get this working. So in order to debug this at first a little bit, let's actually make the LLM cache none, just to kind of make sure our chain is working before we start relying on the cache. So down here, we will have this. One thing I just realized I forgot to configure is we never configured the number of documents to return. So we'll configure that here. We'll have it return 3 documents for each of our queries. And let's see if I defined everything right. And now we should be able to invoke it with something like, who is the mayor of San Francisco? And ideally, that will return some set of documents that will be used to answer that question. So it looks like we're successfully getting that London Breed is the current and 45th mayor of San Francisco. And if we look at our Langsmith trace, we should be able to see some of the documents that actually get returned from that retriever. Where hopefully, so we can see the first one seems to be getting a little bit of a tabular bio. This looks like it might be coming from Wikipedia, which looks like correct from down here. Here's a document that is coming from sf.gov, and here's one that's also coming from sf.gov. And they kind of unanimously declare that London Breed is the mayor of San Francisco, which is good and correct for our cases. So now let's add back our semantic cache of our semantic cache, and let's clear it just to be safe, because we don't want it to cache some of the prior responses that we had. And now let's try running this again, where we can ask who is the mayor of San Francisco. It's going to run the retrieval step, which is not cache. One of the key things to remember is that the retrieval step is not cached as part of the LLM cache. It is only the input and output to the model. And let me make sure I'm not going to completely run out of battery. So we get that our mayor is London breed. And then if we run that again, so this will not experience as much of a performance speed up as our prior example, because we still need to run that retrieval step because that one is not cached. So if we run that again, it actually looks like the retrieval step is pretty quick, but then we're still spending 0.8 seconds on that retrieval step, and then the output of Anthropic is going to be exactly the same, just because our retriever is getting kind of those exact 3 documents again, because it's the exact same query. But then our chat Anthropic step is going to take 0.32 seconds instead of 6 seconds, which it did in the prior step. So that is kind of LLM caching in a nutshell. Now let's talk about some of the challenges with a RAG-based application and using that in an application like this. So we can actually change our query here. So in our prior example, we were able to change our query from where does Eric work to kind of where does Eric work with a period. We can try that one again. This one might actually work. So let's see if that does anything. Yeah, so that one still is retrieving the same set of documents. But you could also imagine us using some sort of query like who leads, well, I guess that's a little bit ambiguous, but the mayor of San Francisco is whom? Which semantically is very similar. And so if we were to just produce an embedding of this string alone, it would likely get a lookup. But in this case, we're actually going to retrieve a different set of documents. So if we look at our Langsmith trace, we're going to see that instead of the kind of Wikipedia article, sfgov, our retriever is getting a different section of the Wikipedia article. So it's kind of leading with from Wikipedia. It's the second entry is actually also from Wikipedia. Looks like this is actually kind of similar to what the first document was in the prior example. And then the third document has actually become the second. So even slight differences where now when we format our prompt template, we're going to get this as the input to our LLM versus we can actually open the old one, which is going to be slightly different, where here our prompt is going to get formatted as like these entries in that order. And because those two inputs are sufficiently different, the semantic cache is not going to be able to look those up. So the really important thing to remember there, and I'll kind of emphasize this on my diagram, is that the semantic cache is only caching over here. It's only caching the model inputs and outputs, and even though your question might be similar. So you could also imagine a world in which we had a cache that's actually caching this whole flow, where if you had a similar enough question, it would kind of look up the entire response of the entire chain. This is not what LLM caching does. This is not LLM caching. This is something you can implement yourself as well, but the really important thing to remember is because we're relying on the retrieval step to return the exact same set of documents, we actually have kind of another point of getting a cache miss than if we were to be indexing the entire flow all over. So that's kind of one of the gotchas of using LLM caching in a RAG system like this, but it is still kind of a cool approach, and it works very well with MongoDB. So kind of in summary, today we went through kind of using semantic caching in kind of two simple applications. The first just being a prompt in LLM, kind of mimicking some sort of ChatGPT or kind of custom prompt chatbot. And then we went down into a RAG implementation where the retrieval step was able to produce some cache hits if we gave the same query again, but actually slight differences in the query, even though they were semantically similar, resulted in different documents being retrieved and still produced a cache miss, as one of the gotchas of semantic caching. Thanks for listening, and have a great rest of your day.